This lesson goes through section 9.7 in your text. First, let's remind ourselves of some things that we've already learned about factoring. Factoring answers the question, what things do I multiply together to get this? So if we're factoring 36, we might factor it into 6 times 6. If we're factoring 3x, we might factor it into 3 times x. If we're factoring 6x squared, we might factor it into 3 times 2 times x times x. In all these cases, I rewrite a product as a list of the factors that multiply together to give you that product. We've also said that we can think of factoring as like running the distributive property in reverse. So for example, if I have this expression 9 plus 10, I could factor a 10 out of both of those numbers. I could pull that 10 out in front of the parentheses and leave 9 plus 1 behind inside the parentheses. If I have an expression like 4x squared plus 2x, I can undistribute, I can factor out a 2x from both of these terms, and I pull that factor out to the front outside the parentheses, and I have 2x times the quantity 2x plus 1. If you use the distributive property to check, you can see that 2x times the quantity 2x plus 1 is the same thing as 4x squared plus 2x. It's just written a different way. Remember some tips for factoring that we looked at. The first thing we wanted to do was to break each term into its factors and see if there were any common factors we could take out of both terms. So in this example, 3x squared y squared, I rewrote that as 3 times x times x times y times y. And 6xyz, I rewrote as 3 times 2 times x times y times z. And now I'm looking to see, do these two terms have anything in common? Well, they both have a 3, so I'll be able to factor out a 3. They both have an x, so I'll be able to factor out an x. And they both have a y, so I'll be able to factor out a y. So I take these common factors, 3, an x, and y, and I undistribute them. They come to the front. They come outside the parentheses. What's left behind? In the first term, I still have an x and a y left behind. They stay inside the parentheses. In the second term, I still have a 2 and a z left behind, so they stay in the parentheses. This is a simple way to factor out any common factors between two terms. The key idea for this section is that if you can spot one of those special patterns that we learned about earlier in the chapter, it can make factoring a lot easier. Let me show you what that looks like. One of the special patterns we learned about was called the square of a binomial. We said that if we had a plus b, that quantity squared, we got a squared plus 2ab plus b squared. Here's an example of an expression that starts out in its unfactored form. 4x squared plus 12x plus 9. I notice right away that the first and last terms are both perfect squares, and so I suspect that maybe we can use the special pattern to factor this. In our special pattern, the a in the pattern is 2x, and the b in the pattern is 3. Where did the 2x and the 3 come from? Well, 4 times x squared can be rewritten as the quantity 2x, the whole thing squared. 9 can be written as 3 squared. So we can see how a in the pattern goes with 2x in this example, and b in the pattern goes with 3 in this example. Once we know what a and b are, it's really easy to write the factored form of this expression. The pattern tells us that the factoring is simply a plus b, the quantity squared, and so we replace a with 2x and b with 3, and there it is. That's the factoring. We can also do this using our area model. If we know that in this top left-hand square, we need 4x squared, and in the bottom right-hand square, we need positive 9, we can think of that positive 9, we can rewrite it as 3 squared. and the 4x squared, we can rewrite that as the quantity 2x squared. Now we know that our factors for that first square would be 2x and 2x, and the factors for the bottom right-hand square would be 3 and 3. This is the A and the B in our pattern. So the way we factor 4x squared plus 12x plus 9 is into 2x plus 3 squared. And we see when we do that, it does make our middle terms work out correctly. We end up with 6x plus 6x, which is 12x. How do you spot if one of these special patterns might be at work? Well, a good thing to do is if you notice that the first and last terms are both perfect squares, then you might want to check and see if there's a pattern at work. For example, in this case, the first term, x squared, that's a perfect square. That's just x times x. The last term, 14, that's a perfect square. That's 4 times 4. When the first and last terms are both perfect squares, this is a good time to check and see if there's a special pattern at work. In this case, we're thinking that the factorization here might be x plus 4, the whole thing squared. We'd have to check to make sure that when we multiply out x plus 4, the whole thing squared, our middle term does in fact end up being 8x. Here's another example, 36x squared plus 60x plus 25. These are some big ugly looking numbers, but I do notice that 36x squared is a perfect square. 36 is 6 times 6. And 25 is also a perfect square. It's 5 times 5. So if I think of this first term as the quantity 6x squared, and the last term as 5 squared, maybe the way to factor this is 6x plus 5 squared. To check to make sure that this is right, I would need to multiply this out using either a table or FOIL. When I do that, I would see that both my outer and inner terms are 30x. 30x plus 30x is indeed 60x. So this is the correct factorization. Let's try another one of our patterns, a minus b squared. What's shown here is an expression 4x squared minus 12x plus 9. The only thing that's different here was that in the previous example, we had 4x squared plus 12x plus 9. So the only thing that's different here is one number has a different sign. That 12 in the middle is negative instead of positive. This follows the a minus b squared pattern. In this case, a in the pattern is 2x, and b in the pattern is going to be negative 3. And the pattern is going to make this easy for us to factor. Let's show this one using an area model. 4x squared minus 12x plus 9. Again, we need for this first square to have an area of 4x squared, and the last one to have an area of 9. I'm going to replace that 9 with negative 3 squared. Because remember, negative 3 times negative 3 gives you positive 9. And I know that I'm going to need a negative sign when I multiply this all out. Again, I'm going to replace the 4x squared with the quantity 2x, all that squared. And now I can write the factors around the outside of my area model. 2x times 2x gives me the quantity 2x squared. Negative 3 times negative 3 gives me the quantity negative 3 squared. And when I fill in the outer and inner boxes here, 2x times negative 3 gives me negative 6x. 2x times negative 3 gives me negative 6x. When I add those together, I get negative 12x. And so this is the correct way to factor the original expression. One last pattern to use. This is the difference of squares, where we have two perfect squares and one is subtracted from the other. In this case, I notice that there is no middle term. There's a 9x squared term and there's a constant term, but there is no middle term that has only x as its variable. Right away, this makes me suspect that we might be dealing with a difference of squares pattern. So I notice that 9 is a perfect square, so I can rewrite the first term as the quantity 3x squared. And 16 is a perfect square, so I can rewrite 16 as 4 squared. The a in this pattern is 3x, and the b is 4. So I think that maybe this expression factors into 3x plus 4 times 3x minus 4. And I can check that using FOIL. If we do this with an area model, I know that the first square needs an area of 9x squared, the last square needs an area of negative 16, and the remaining two squares need to cancel each other out. So I know that one of these factors along the side is going to need to be negative, and one of them is going to need to be positive, because the bottom right-hand corner ends up as a negative 16. And I also know that of the two squares that don't have any numbers in them, one of them is going to need to be positive, and one of them is going to need to be negative, because they add up to 0. Now I can fill in the remaining parts of my factors around the outside of my rectangle. 3x times 3x equals 9x squared. And negative 4 times positive 4 gives me negative 16. That means that I end up with positive 4 times 3x, that gives me positive 12x. And 3x times negative 4 gives me negative 12x. The positive 12x and the negative 12x cancel each other out. And in the end, we end up with 9x squared minus 16. So how do we use special patterns to factor? Well, I've showed you how to recognize those special patterns, but sometimes they're a little bit harder to spot. Let's say that I asked you to factor 3y squared minus 48. 3 isn't a perfect square, and 48 isn't a perfect square. But here's what I do notice. 3 and 48 have a factor in common. They both have 3 as a factor. So I could factor 3 out of both expressions. I would have 3 times y squared minus 16. The stuff inside the parentheses now does follow the difference of perfect squares pattern. So now I can look for that special pattern. In this case, the special pattern is the a squared minus b squared pattern. So the stuff inside those parentheses can be rewritten as y squared minus 4 squared, which I can factor using the special pattern. So I have 3 times y plus 4 times y minus 4. So let's summarize a little bit about what we know. What do we do to factor second-degree polynomials? That's polynomials that have an x squared term in them. So here are two different examples of things we've learned how to factor so far. And we have a couple of different approaches. One is we can look to see if there are special patterns at work. One is we can ask ourselves, what are the factors of c, the constant at the end, that add up to b, the number in the middle? We will also be learning what do we do if that leading coefficient, the number in front of the x squared, isn't just 1. So far everything we've done, either we can use a special pattern or the leading coefficient is 1. We'll get to this a little bit later. Remember, always look to see if there are any monomial factors, any common factors between all of the terms first. Then look for special patterns or ask what are the factors of c that add up to b.